this is just an overview of Year 13 Physics, DC and Capacitors for NCEA Level 3. Okay, internal resistance. The chemicals in the battery all use up some energy that each coulomb of charge gains when they enter the battery. So there will always be a potential drop, or some energy is used up by the internal resistance. Now the EMF, or the claimed voltage, is actually the voltage across the terminals of the battery when no current flows, or when it's short-circuited, or when the battery is not supplying energy to light a lamp or heat a resistor. It's also the energy gained by each coulomb of charge that enters the battery. So this is a symbol for a battery with its internal resistance. That's your EMF, that's the internal resistance. This is the outside load. So the formula that is used for a battery that's discharging or supplying energy is given by the total voltage is the sum of the voltage across the outside load plus the voltage or the potential drop across the internal resistance. Okay, this V is called the terminal voltage, and that's a voltage available to the external circuit, and your terminal voltage V is equal to I times R. Okay, now when cells are being discharged, that's a formula you use, but after some time batteries become flat or they have no more energy left, so they need to be recharged if they're the rechargeable ones. For that, what happens is as batteries grow old, the internal resistance becomes quite big. So in order to charge it, you need a charger, and the important thing here is that the positive terminals are connected together. So the current is actually flowing the other way compared to what happens when it's discharging. Okay, so this is the only occasion where the terminal voltage is greater than the EMF. When it is discharging, the terminal voltage is always less than the EMF. This is one case where the terminal voltage is greater because that's at a higher potential. Moving on to Kirchhoff's laws, these are used in parallel circuits where you have multiple sources of power in different branches. Kirchhoff's laws are two of them. There's Kirchhoff's current law, and because current is a flow of charge, it's to do with conservation of charge. So this has to do with what happens at a junction. So this is your junction where you have more than one pathway. So the total current entering the junction is equal to the total current leaving the junction. And the other one is Kirchhoff's voltage law, and it has to do with a closed loop. That means there's no break in the circuit. So the total voltage around a closed loop equals 0. This is because you have the 9 volt which is supplying. This 9 volt is used up by the components in the circuit. That's essentially what this means. So here's an example of how Kirchhoff's law is used. So let's make it big. So here are 3 different currents. I've just color-coded the different currents. There's one current here through that branch. There's another current flowing this way through this branch. And there's a third current through that branch. So the question is, how do you find the sizes of all these currents? So the first thing we do is write a current equation. So the total current coming into the battery, into the junction, is equal to the total current leaving. So that's how I got this one. And then you use any of the loops. So I've used this loop to calculate what is the voltage equation to calculate the size of I1. So just remember that's resistance. So the way that I do is imagine you're going through the wires, and let's say you're going clockwise. So you're looking at the voltages. So the voltage across this resistor is resistance times current. And now, because I'm going against the flow of current, I need to add it because there's more energy there. And if you're coming out of the positive end of a battery, don't worry about the direction of the current. That's going to be positive. So you're going this way, plus 6, and nothing here. When it comes here, you're going out of the negative, so it's minus 20 volts. So that's how I got this over here, and that's how I got value for I1. Similarly, I used that loop, and I got the value for I3. And then I used the current equation there to get the total current. Moving on to capacitors. So we're looking at parallel plate capacitors, where you've got a set of parallel plates separated by an insulating medium, and that is called the dielectric. Now, the way you charge a capacitor, the easiest way is to connect it to the terminals of a DC supply. And when the capacitor is fully charged, four things happen. The current stops, each plate gets an equal but opposite charge, and you get an electric field built up between the plates, and the strength of that electric field is voltage across the capacitor, which is the same as a supply voltage, divided by the distance between the plates. Okay, and then there's a word called capacitance, which has to do with the amount of charge a capacitor can store when the voltage across the plates is 1 volt. And this is an important formula. Capacitance is Q over V, and the unit for capacitance is farad. Now, there are other units like microfarad, nanofarad, and picofarad. So you need to know the conversion. So micro is times 10 to the power of negative 6. Nanofarad is times 10 to the power of negative 9. And picofarad is times 10 to the power of negative 12. So they're all multiples of 3. Okay, moving on. So capacitor construction formula depends on these three things. It depends on the area of the plates and the distance between the plates. So bigger the area, the more charge it can store, and the closer the plates are, again, the more charge it can store, so greater the capacitance. Now, the constant of proportionality is this, which is called the absolute permittivity of free space, and it has a value 8.84 times 10 to the power of negative 12 farads per meter. This will be given to you. And this other one all depends on, is it air that's in between the plates, or is it some other insulating medium? So that's called the dielectric constant. It's also called the relative permittivity. They mean the same thing. If it is air between the plates, then it is 1. So dielectric constant, how do you measure it? It's a ratio of two capacitances. So it's a ratio of the capacitance with the dielectric divided by the capacitance with air. So there's no unit. Okay, and the moment you introduce a dielectric other than air, the capacitance increases because it can store more charge. Then moving on to how you can connect capacitors in series or parallel. So here are your two formulae. This tells us when you connect capacitors in series, the total capacitance decreases, but when you connect them in parallel, the total capacitance increases. Moving on to energy stored in a capacitor. So the cell supplies the same amount of energy to every coulomb of charge that enters the cell. So voltage, a graph of voltage against charge is a straight line, saying the voltage supply is constant. The area under the graph line is the energy that is supplied by the cell, and in this case for the cell it's Q times V, it's a rectangle. But a capacitor plates that are not charged at the start, is no voltage across it. But as more and more charges accumulate on the plates, the voltage across the capacitor plates increases till it becomes equal to the supply voltage. And so the area under this is only half QV. So what's happened to the other half of the energy? It's actually lost in the form of heat due to resistance in the wires. Now, coming on towards the end. So what happens when you charge and discharge a capacitor? Looking at current time and voltage time. So the circuit current, once a capacitor is fully charged, the current drops to 0. So this is a decay curve. Whereas while you're charging a capacitor, the voltage across the capacitor goes from 0 to a maximum. So these are both exponential curves, and that brings us to the concept of time constant, and for a capacitor, tau equals RC. Now, what is this time constant? It's the time taken for the current or the voltage to change by 63% of the maximum value. It's also, if the rate had not changed, how long would it take to charge or discharge a capacitor? Ideally, it takes about 5 time constants for a capacitor to be fully charged or discharged. These are for while it's charging. Okay, when it's discharging, they're both decay curves because both the voltage and the current will fall to 0. Theoretically, because these are exponential curves, this is called an asymptote. It only approaches 0, doesn't quite reach it. Now, if you're asked to calculate the voltage at some after a particular time constant for growth curves, this is your formula. For a decay curve, current or voltage, that's your formula. This is your exponential button, and the n is number of time constants. The last part, what happens when you connect pre-charged capacitors together? So this one's where they're connected in parallel because the positive plates are joined together. So that's two different capacitors charged, so they have a voltage across them. So what actually happens is charges flow between the capacitor plates until a common potential or a common voltage is reached. So what you need to do first of all is find the charge on each capacitor, and then you find the common voltage by doing total charge divided by total capacitance. And in order to calculate the new charge on each capacitor, it's the capacitance doesn't change, but the voltage has changed. So that's how you get that. And the thing to remember is that in this process, there's no charge loss, so you can account for every charge. However, some energy is lost in the form of heat due to resistance in the wires. How do you calculate the energy? It's the total energy at the start minus total energy after connecting. And because energy is half QV, so that's how you get the total energy at the start. So you've got V1 and V2, which is different. And then the total energy, this is the same because it's a common potential, but Q1 and Q2 is a new charge that's accumulated. So I will